Oh, excuse me, just got to get this going. I'll get back to this later.
3, 2, 1. Contact is the secret, is the moment when everything happens. Contact. Let's make contact. 3, 2, 1. Classroom. Contact.
They're habit forming.
Diamonds, rubies, sapphires, emeralds, amethyst, sulfur, pyrite, quartz, selenite, and salt. All are crystals. There are thousands of different kinds of crystals. Lots of things are made of crystals. Crystals have two things in common. One, they all grow. Some grow quickly, in just minutes. Some grow slowly, over millions of years. The second thing that crystals have in common is they all have habits. Crystallographers, that's people who study crystals, use the word habit instead of shape to describe the shape of the crystals. They would say salt crystals, and those are salt crystals, have cube habits. Pyrite also has a cube habit. Wolfenite has a flaky habit. How would you describe this crystal's habit? And how about this one? This is a quartz crystal. It is made of billions, trillions of molecules. Molecules are the smallest part that make up a crystal. Molecules come in many different shapes, and they can only fit together in certain ways. Let's say I'm a molecule with 4 ends. 1, 2, 3, 4. Where other molecules can attach. As they attach, the crystal begins to look like this. Another kind of molecule might be shaped like this. The pattern of the crystal would look like this. What if the molecule had 2 ends like this? The pattern of the crystal would look like this. Of course, crystals don't grow flat. They grow in all directions. Like this one, see? They grow this way, that way, all directions. Let's see how this is coming. Yep, the crystals are forming around the string. I'll come back to this later. Stick around. You know, there's one type of crystal I haven't told you about. And I'm all set to take a picture of it. Temperature's just right, the clouds are just right. Snow, that's what I'm going to take a picture of. You know, there's many different kinds of snowflakes. There's the plate, the stellar crystal, the column, the needle, the spatial dendral, the cap column, the irregular crystal, gravel. Fancy names. But star-shaped crystals like these are the hardest ones to find.
You know, taking pictures of snowflakes, it isn't easy. But this is serious. You know, snowflakes are one of the hottest things in science today.
Snowflakes are being studied here at Boston University in the physics department. I'm going to visit Professor Eugene Stanley, who's an expert in how snowflakes form.
Can't be true.
When I got to his lab, his two kids, Rachel and Michael, were arguing about whether two snowflakes could ever be exactly alike.
Well, let's just ask my dad, okay?
Oh, hi, Stephanie. How are you?
Mr. Stanley?
Call me Gene. Actually, it's a good thing to argue about because it's one of those things that no one knows the answer to. There are many different views. And in a sense, you're both right because snowflakes are not completely understood. Now, some crystals are understood where we know the rule very well. Take, for example, salt. Every day you see salt on the table. And people know that the structure of salt obeys a simple rule. There's a chlorine that's blue and a sodium that's red. And then a chlorine that's blue and a sodium that's red, one after the other. All through here, it's regular and repeated. Does this look like a snowflake to you? No. Not at all. Snowflakes are almost the opposite extreme. They're random, aren't they? Each one has some detail of it that's different than the other one. And that's because it formed a totally different way. Why? Because
Gene explained that snowflakes form in the clouds. Water molecules are tossed about by moving air.
Snowflake. That helpless little snowflake is up in those clouds, bouncing around left and right. There is no way the water molecules in that snowflake can arrange themselves so perfectly, is there? So we have to find a different rule. Now, where should we start? How can we find a rule that describes how snowflakes are made?
Using a computer, Professor Stanley can see how water molecules attach to each other to form a snowflake.
The computer program shows the motion of each individual water molecule as it bounces around just like you would bounce around if you were in a hang glider in the sky. Can you guess where that water molecule is going to attach to the snowflake? Can you, Michael? Where do you think?
Looks like attaching to the ends.
To the tips, you're right. So this computer program shows how the snowflake is actually assembled, molecule by molecule by molecule. It's the opposite extreme of our simple salt crystal, which moves very regularly, one to the next, to the next, to the next. This moves all over the place. You don't know where this is going to go next, do you? That's the essence of snowflake formation. It has to do with the chaotic motion of the water molecules up in the clouds.
The computer can show in a few seconds what takes much longer in the clouds, the formation of a snowflake. Each color represents a new group of molecules attaching to the snowflake. The middle of the flake is shown in white. The first group that attaches to the edges is shown in blue. The next layer is shown in purple. Notice the red group. Only a few molecules from that group found their way into the center of the flake. All the rest grabbed on only around the edges.
And that's why a snowflake has a very light, feathery structure. If the particles, on the other hand, were able to go deep down inside, this could become as dense as that sodium chloride salt crust. But this doesn't do that. Now, is this a completely chaotic pattern, or do you see something? What do you see, Rachel, in this still?
There are 6 arms.
You're right. And you also see something about these side branches, don't you, Stephanie?
Yeah.
Are they usually opposite each other? Like a tree? Like a little spruce tree, maybe? Or a hemlock tree?
Yeah, these are like leaves, sort of, and they're like stems
That's right.
connecting.
And all the snowflakes had that pattern, or most of them at least, even in the book you were looking at when we first started.
If each one forms differently, how come they all have 6 arms?
That's a good question. No one's really quite sure of the answer of that, but it probably goes back to the structure of the molecules that's making this up.
Water molecules are shaped like boomerangs. As they freeze, they grab onto each other. The shape they make is a hexagon.
And a hexagon has how many sides?
6.
And how many arms in a snowflake?
6.
Do you think there might be some connection, maybe?
Yeah.
You're absolutely right. So something that's going on at a tiny molecular level can be reflected in this macroscopic structure. So up in the clouds, two things are going on simultaneously. The water, on the one hand, wants to be chaotic, and on the other hand, the water wants to be ordered. So the snowflake you see is a kind of resolution of two things going on at the same time. That often happens in science. Science doesn't just have one answer, it has sort of two answers. So is it true that no two snowflakes are exactly alike? No one knows the answer to this question for sure, because there's so many possible variations in the random arrangement of water molecules in a snowflake. The chance that you'd find two identical snowflakes is very, very remote.
The structure of the crystal is the same as the structure of the first molecule it comes from. Crystals are nice, neat clumps of molecules, like the one I made. Look at it. Hey, can you imagine the shape of the molecules that make it up?
The shape of a crystal comes from the shape of the molecules that make it up. That's called the crystal's habit. Crystals have very regular habits. Snowflakes have a 6-sided habit, but each one is different because snowflakes are formed in the chaos of the clouds. 3-to-1 Classroom Contact is a production of the Children's Television Workshop.